Here's the second part of the finding volumes methods in calculus. This time we're going to do something called the method of cylindrical shells. So let me write that out. You'll see why cylindrical in a minute. The idea of what we're doing is no different than last time. We're just going to look at it in a slightly different manner. And plus, last time most of our rotations were about the x-axis, or the axis of revolution was the x-axis, which was a horizontal line, or some other horizontal line for the most part. In this, we're going to focus more on vertical lines, and this method involves these shells. So let me go ahead and start with an example. Consider the region in the fourth quadrant bounded by the graph of y equals x cubed minus x and the x-axis. Determine the volume of the solid that results from rotating the region about the y-axis. So things are a little bit different this time. Once again, first thing you always want to do is get a picture of this thing and get the region down. So let me go ahead and draw just a rough sketch of the thing. You should recognize it as an odd function. You can go to your graphing calculator if you need to see it, but it comes in and mostly it just does something like this. It's an odd function. It goes about like that. We are interested in the stuff in the fourth quadrant that is bounded by this graph and the x-axis. So we're down here. This is the fourth quadrant. Here's the x-axis. There's the graph. So they are talking about the region in here. And you can use your calculator. You can set the function equal to 0 to find these, but you'll find that the zeros are at 0 and 1. So let me blow that picture up for my next drawing. I really don't care about this stuff. But it's down here like this. It ends at 1. There's our region. And we are revolving it around the y-axis this time. So the axis of revolution is a vertical line. Now, if you try to do the washer method, you would want to do horizontal washers because it's only going to form a washer if it's in that shape, in that format, horizontal. The problem here is that you have the same function for what you might call upper versus lower, and they would subtract each other off. So I can't use that method right there. I'm destroyed. So let me go ahead, take that out of there. and introduce you to another method. Instead, this time we're going to look at vertical things like this. If you'll remember, one of the things that we did in Calc 1 when we were doing the Riemann integral, we were constructing Riemann sums, these rectangles, and the right hand ones are the ones that I'm using right now. You go to the graph and then something like that. So there they are. As before, I'm interested in just one of these things, but let me just, for the time being, let me remind you there's x0, there's x1, this here might be x sub k, and say this might be x sub n would be equal to 1. And then if we're going to revolve this around the y-axis, this little piece in here is going to become a little cylinder. This piece right next to it is going to become a concentric cylinder, so I guess we might do something like this. It's bigger than the other one with that being inside of it. And then I have an even bigger cylinder here for this next one, although they're going down like this. So you might see it's getting hard to draw these, but hopefully you can see that that concentric cylinders are going farther and farther out until I get to the very last one at the end there. Then the idea is we're going to take the volume of all these cylinders, add up the volume, of these n cylinders, and then let n go to infinity. The reason why is then you're going to evaluate an integral. So let me show you how you work this kind of a thing too, as far as the formulas that are needed and everything like that. As I have always done, instead of trying to get a formula and adding them all up and actually doing this stuff, it's better to just get a handle on one particular x and work with it. And then you can go right to the integral anyways. So another time I'm going to graph this again. There it ends at 1. What I'm going to do is consider one of these rectangles that is at x. Now, if we are revolving this around the y-axis, as I mentioned, you're going to get yourself a cylinder. So let me draw such a cylinder that you'll get. Now, the difference here is that the cylinder walls are the things that will be delta x. So this distance here, from here to here, that will be delta x. The height, let me just, for right now, let me call that h. And then we also have, don't forget, this is a cylinder. So that means all the way around here is a circle. A cylinder is known by the height and the radius. What is the volume of this particular cat? Well, I think the easiest way is to take this and open it up. Say you slice it with a pair of scissors and open it up and roll it out. You'll have something that looks like this. And of course, delta x is how thick these are, so this length or this width up here, is delta x. If I want to know the volume of this thing, well, I'll need to know all three dimensions. Right now I only have the thickness. Well, here's h again. And down here, how long is that? Well, remember, this line is the same as the length of the circumference of this circle down here. Well, this circumference down here is 2 pi r. So what you're going to end up, if you look at the volume of a shell, will be the product of these three dimensions. So you have 2 pi r h delta x. So as before, we're going to go ahead and change these r's and h's involving x's. So let's see how they work in this particular problem. If you look, let's take a look first at the radius. The radius is how far the particular shell wall is to the origin. So the distance from here to here is going to be r. And of course, that's no difference than x. Or if you want, that's x minus 0. That's just equal to x. So this equals 2 pi x. Now what's the height? The height is the vertical line y equals 0 minus, well, what's at the bottom of this thing? The graph. So I'm going to take 0 minus whatever that equation was again, or that the function was, x cubed minus x. So you're going to get, I'll put this in a block right now, 0 minus x cubed minus x. This equals 2 pi x times, I'll go ahead and simplify a little bit in here. I get x minus x cubed, which equals 2 pi times x squared minus x to the fourth. The only reason I'm doing that is because it'll make the integral easier. And then all these have a delta x attached to them. Apparently I'm still struggling with this. So if I want the volume of the solid, well, it's easy then. Copy this. I get 2 pi. The integral went from, where did x start? X started when x was 0 and ended when x went to 1. 0 to 1. X squared minus x to the fourth dx. Not much here. I think I'm going... I feel like I would offend you by actually finishing this problem, so let me go ahead and just write the final answer and you can check it out for yourself. I get 4 over 15 pi. Alright, let's move on to the next example. Consider the region in the plane bounded by the curves y equals x squared minus 6x plus 10 and y equals negative x squared plus 4x plus 2. Determine the volume of the solid that results from rotating that region about the y axis. So once again, take a look at the graph. Go ahead and use your calculator to get a graph of them. I don't really care about it that much, other than it all happens to be in the first quadrant, and they're both parabolas. One goes like this, the other one kind of goes like that. You should be able to tell from my graph which is the upper and which is the lower. The upper one is going to be the negative x squared because those aim downward. So this one on top is y equals negative x squared plus 4x plus 2. And then down here, this one is y equals x squared minus 6x plus 10. And obviously the region that's bounded by these graphs is in here. Every other region is infinite. So the region they're talking about then is inside of here. And as with anything else, we need to know where it starts and where it ends, because that's where the limits of integration are going to be. Oh, I gave that one away. Oh, go back. How do you find those? Well, you set them equal to each other. So let's first find these points. So let's find the limits of integration. Well, let's set them equal to each other. We're going to have negative x squared plus 4x plus 2 equals x squared minus 6x plus 10. I'm going to take everything to the right hand side, and I'll get 0 equals 2x squared minus 10x plus 8. For convenience, I'm going to divide everything by 2 to get 0 equals x squared minus 5x plus 4. This is very easy to factor. I'll get x minus 1 times x minus 4, and so you get x equals 1 and 4. So my limits of integration will go from 1 to 4. Okay, let me redraw my picture so that I can draw my rectangle. Now, we are revolving around a vertical line. In particular, the y-axis is a vertical line. So we're going around that thing. There's our region. What I'm going to do is once again draw a rectangle to help me out. Because if you look at that thing, when that spins around, it's going to create a cylindrical shell. So I don't think it's such a bad idea to draw that. I'll draw it with some better effort than what I put into it. Go like this. So once again, we're going to get a delta x. What you need to get then is the radius. You need to have that, r, and you need to have h. Remember, when you roll that thing out, it's a thin, I don't know what you'd call it, thin piece of carpet, whatever. All that matters to me is I get the relevant information down here. This part here, the thickness of the thing is delta x. That corresponds to this here, delta x. It's always a good idea to center these at x. X is clearly going to move from 1 to 4, so as x moves from left to right, you can see the rectangles increasing in size and then decreasing back down. What is the height of this thing? Well, the height is going to be this function, the upper function, minus the lower function. So let me do that. H equals, what was the upper function? Let's do upper minus lower. These are upper function minus the lower function. The upper function was negative x squared plus 4x plus 2, and the lower function was x squared minus 6x plus 10. this ends up equaling negative 2x squared plus 10x minus 8. So let me put that there, I guess. Negative 2x squared plus 10x minus 8. And then, of course, down here, this length, the length of the base, is 2 pi r. So I have 2 pi, and what is r? Well, r is the distance from here to the center. So once again, x minus 0 is just x. So you get 2 pi x. All right, so the volume of a shell equals, multiply these three things together, 2 pi x times 2x, negative 2x squared plus 10x minus 8 delta x. Now I'm going to do something that I don't know how you're going to feel about it, but I'm going to factor out a negative 2, and I'm also going to multiply through by x all at the same time. So I'm going to get negative 2, I just said I'm going to take out a 2, negative 4 pi times x cubed, I said a negative 2, so that would leave a negative 5x here, so negative 5x squared. And then if I took out a negative 2, that'd be plus 4 times x would be plus 4x delta x. So the volume of the solid V equals negative 4 pi. The integrals we said went from 1 to 4. We have x cubed minus 5x squared plus 4x dx. And as you can imagine, I'm leaving this to you also. Check it out. This will end up being 45 pi. Here's an example that lends itself easily to volumes of revolution. And it goes like this. Suppose a sphere of radius 6 has a vertical hole of radius 3 drilled right through the center. Compute the remaining volume. So, what's happening here is we're going to start with a sphere, radius 6, and then what we're going to do is come in here and drill a hole. So it's going to cut off this, come through, and then cut down here as well. So what you'll be left with is a sphere with a hole right through the heart of it. Now, a lot of people think that what you take out is simply a cylinder. If you don't think about it very much, you'll think that what comes out of there is simply a cylinder. And that's not the case, because a cylinder has a flat top and a flat bottom. This does not have a flat top. This is a sphere that it's drilled into, and it does not have a flat bottom. That makes a difference. This cylinder, if you were to get it right, would have to have a little bit of a top, and this bottom would have to have a little bit of a bottom. I find that very difficult to draw, so it is not a cylinder. So let's make a note of that. Not a cylinder that is drilled out. Well, what we could do is instead look at just a circle of radius 6. The equation of a circle of radius 6 is x squared plus y squared equals 6 squared. Of course, this means the circle is centered at the origin. But believe me, you don't want to mess around with changing that around. In other words, I get x squared plus y squared equals 36. Now, if you graph that, you, of course, will get a circle of radius 6, 6, 6, negative 6, negative 6. This is way more than we need for our purposes. So what I'm going to deal with is instead just the first quadrant. So let's deal with that. I'm going to take that one away. Not that. And I'm going to deal with just the part that occurs in the first quadrant, the circle. There's more to it than that. I don't want, well, when I talk about a volume of revolution, I'm going to be revolving something around, in this case the y-axis. But I don't want to revolve this thing around the y-axis because it doesn't have the top chopped off of it. So I need to work that into the problem somehow. Let me take this, can I take, it probably will take the whole thing out, which it did. But really, what we have going on here is from 3 to 6, this is what's left over. But the stuff that's chopped out is there. So really, if you look at it, this region here is the region that we could revolve around the y-axis. Then I could multiply it by 2 to take care of the bottom half of this thing. So keep that in mind. What I'm going to do in order to find this volume is I'm going to revolve just this region around the y-axis. That'll give me the top half of the drilled sphere. And then I'll multiply by 2 to get the bottom half. So we're going to be taking this around, and like you do every other time, get yourself a rectangle centered at x. And of course its thickness, as always, is delta x. So let's take a look at what we need. The radius that we need in our formula extends from x to the origin. So r equals x. The height is this function minus this function down here, which is just 0. The y value of this function up here, though, is the square root of 36 minus x squared. That comes from this equation here and solving it for y. And a good reason to only work in the first quadrant is so I don't have to worry about plus or minus and that kind of business. So remember, the equation of that graph is y equals the square root of 36 minus x squared. All right. So the volume of a shell, that equals 2 pi r h delta x, which is 2 pi, r was x, h is that stuff, delta x, and this lends itself very nicely to the volume of the solid. And the integral, I think, was at 3 to 6. It goes from 3 to 6. Why was it 3? I think I don't remember mentioning that. It's 3 because the radius of the hole being drilled was 3. So that accounts for the hole being drilled. So then I have x times the square root of 36 minus x squared dx. Of course, to do an integral like this, hopefully you recognize that this piece inside of here is a nice thing to allow u to equal. That way you get du equals negative 2x dx. But I don't need negative 2x, I need x. Here, this will be the square root of u, right here. So I've accounted for this piece, but I only want x dx, not negative 2x dx. So it's easy enough to do this. Negative 1/2, and then get rid of that piece. So the volume equals 2 pi the integral. Now remember to change your limits of integration when you switch to u. No, you're no longer using x, you're using u. So let's take x equal 3, plug it in right here. What is 36 minus 3 squared? Well, it's 36 minus 9 is 27. And then plug in 6. 36 minus 6 squared is 0. That's nice. Now let me go ahead and replace these. X dx I had, but let me do that part right there. This is going to be the square root of u, but it's better to put it as u to the 1/2. And then x dx was equal to negative 1/2 du. I'm going to do a little bit of simplifying. The 1/2 I bring out, I get a negative pi. The integral goes from 27 to 0. U to the 1/2 du. And of course, hopefully you remember that I can turn the limits of integration upside down if I make it the negative of the integral. All right, now I'm ready to work it. Not much here to do except remember that u to the 1/2 when you integrate it is 2/3 times u to the 3/2. So I'm going to get 2/3 pi u to the 3/2, and that's going to go from 0 to 27. And I will leave this to you to see that it equals 108 radical 3 pi. All right, there was an error right here. I forgot to multiply this by 2. So throughout, change that to a 4. Then this becomes negative 1/2 pi. This becomes pi over 2. Sorry. That becomes negative 2 pi. Pi. Four-thirds. And now everything will work out just like the answer says it will. Consider the region in the plane bounded by y equals 5 and y equals x plus 4 over x. Determine the volume of the solid formed by revolving the region about the line x equals negative 1. Let's start with, let's see, here's y equals 5. That's a horizontal line. Okay, and then y equals x plus 4 over x. So what's that look like? I can't let x equal to 0. X equals 0, it must be doing something like this. When x is going to 0 from oh, here it goes. It must be going. Use your calculator to help you out with this. I'm trying to figure out on the spot, though. Something like this. And then it comes up and eventually hits it again. So let's find out where this equals 5. So we have x plus 4 over x equals 5. I'm going to multiply everything by x. Evidently, it's in the first quadrant. So I'm going to get x squared plus 4 equals 5x. Oh, this is nice. X squared minus 5x plus 4 equals 0. X minus 1 times x minus 4 equals 0. And we get x equals 1 and 4 like we had before. Nice. So 1, 4. Now let's go ahead and draw that picture again. But now let me put this, there's 5. And I don't care much about what the graph looks like. All I care is that it hits in a certain spot and hits in another spot. There would be 4, let's say, and there's 1. This is the region. And we are rotating it about x equals -1. If you're going to ask me to scale anything, you're in for some bad news. All right, so there we go. There's my setup. Let me go ahead and draw the rectangle that I'm going to use for this problem. Once again, that rectangle is of delta x. Centered at x, delta x thick. And let's go ahead and get the radius. So if my r stretches from x to here, you can see that it's going to go, x would be to 0, but then I have one more. So I have x minus -1. Let's put it down here. R equals x minus -1, which equals x plus 1. And the height is, the top function is y equals 5, and the bottom function is this parabola. So the h equals 5 minus, let me remind myself of what it was, x plus 4 over x. And that's simply going to equal 5 minus x minus 4 over x. All right. Then I am ready for the volume of a shell. Equals 2 pi r, which is x plus 1, h, which is that thing, 5 minus x minus 4 over x, times delta x. I think I might find it useful to multiply this all out. So x times 5, I'll do x and multiply it through everything. So I'll get 5x minus x squared minus 4. And I'll go ahead and do 1. I'll have 1 times 5 is 5. 1 times -x is -x. And then 1 times -4 over x is -4 over x. So that leaves me with 2 pi times 4x minus x squared plus 1 minus 4 over x delta x. And now we're ready to integrate. So the volume of the solid is given by v equals 2 pi. The interval, as I said, was going from 1 to 4. I'll get 4x minus x squared plus 1 minus 4 over x dx. So that's 2 pi. 4x squared over 2 is 2x squared minus 1/3 x cubed plus x minus 4 ln. Since x is dealing in positive numbers, I don't have to put the absolute values around it. Going from 1 to 4. That equals 2 pi. Let me go ahead and throw in 4. Let's see, if I throw 4 in here, I'm going to get 2 times 16. So I'll get a 32 for that spot. Then I'll get negative 64 over 3 plus 4 minus 4 ln 4 minus 2 pi times, plugging in 1 now, I'll get 2 minus 1/3 plus 1. Ln of 1 is 0, so minus 4 times is 0 for that piece. I'll simplify each piece separately, so I get 2 pi, let's see, 36 minus 64 over 3 minus 4 ln of 4 minus 2 pi times 3 minus 1/3. That equals 2 pi. That is a horrible looking 3. Let me change that thing. That's terrible. The excitement gets me sometimes. I can do this in my head. If you think of this as 108 over 3, and you're subtracting 64. What is 108 minus 64? It's 44. Minus 4 ln 4 minus 2 pi. Think of this as 9/3, so this will be 8/3. Okay, so let's see what we get. I'm going to get 2 pi times 44 over 3. That'll be 88 over 3 pi minus 8 pi ln 4 minus 16/3 pi. So I can take care of 88 minus 16. Oh, that's nice. That's 72. So I get 72 pi over 3 minus 8 pi ln 4, which equals 24 pi minus 8 pi ln 4. Now, if you are dealing with functions, then use the disk/washer method for horizontal. It's lines like this. Axes of revolution. Cylindrical shells for vertical. Axes of revolution. So that way you have a visual in case you come back to it later on. Horizontal goes side to side, vertical goes up and down.